In this video, we're going to talk about cell potentials and how the composition of our reaction mixture affects that. And before I do that, I do want to do a quick review. We said that we have two driving forces for our electrochemical reactions. Our first one was our cell potential, abbreviated a capital E. We also could call it our electromotive force, right? Cell voltage, all of those things meaning the same. And then our second one was our free energy change. Or delta G. And we had said that they're both directly proportional, but the sign on them is opposite. So my free energy change is equal to negative N F and then multiplied by my cell voltage, right? I have this negative sign here. So if this is negative, this is going to come out positive and vice versa. So my free energy change and my cell potential are directly proportional. But have opposite signs. Remember, if we have a negative sign in front of my free energy change, it just tells us the direction of the energy, right? That is being released versus being absorbed. It doesn't tell us the magnitude. So a negative 3 kilojoules is the same as 3 kilojoules, right? It's just that the negative 3 means it's being given off. If it's a positive 3, it's being absorbed. So I know when I say directly related, it might look like as one gets bigger, right, the other one gets smaller because of that negative sign, but that's not true. Remember, the negative just tells us the direction because I have this equal sign, right, and it's not over the other number, right? They're directly related. So my cell potential and my free energy are directly proportional but have opposite signs, right? A spontaneous reaction is going to have a negative free energy change, but a positive cell potential. So negative free energy changes we know are spontaneous from chapter 16. In this chapter, we learned that it has a positive cell potential if that's the case. And then again, remember N was the number of moles of electrons transferred, F was our Faraday constant. So what we're going to look at here is what happens if I'm not at standard state conditions. So cell potentials, just like free energy changes, do depend on the temperature and then the composition of our reaction mixture. So cell potentials as with free energy changes, depend on the temperature and the composition of the reaction mixture. And by composition of the reaction mixture, I mean concentrations if they're solutions or partial pressures if they're gases, right? So either my concentrations, remember those brackets mean molar concentration, or my partial pressures. So from chapter 16, we had an equation where my free energy change was equal to my standard free energy change, so that not symbol, plus RT, right, my gas constant, multiplied by my temperature, times the natural log of Q. Again, Q is being our reaction quotient. This chapter, we know this equation up above, and if I was to modify that to put my standard state symbols, those not symbols on it, it would also be true. So we know that delta G is equal to negative NFE and delta G naught is equal to negative NFE naught. So what we're going to do is we're going to substitute. I'm going to substitute this in for this number, right, because they're equal. And then I'm going to substitute this in for this number. We're going to do a little rearranging and come up with a new equation here. So we're going to substitute. And I'm going to have negative NFE is equal to negative NFE naught plus RT multiplied by the natural log of Q. I'm now going to divide both sides by negative NF. So when I do that here, right, those are going to cancel. Here, negative NF, those are going to cancel. And then here, I'm going to have my negative NF, which I'm going to bring the negative up. So we're going to have E, right, negative NF cancels, is equal to E naught, negative NF cancels again, minus RT over NF times the natural log of Q. And this is called the Nernst equation. And we can use it to calculate our cell potential at non-standard state conditions, right? Or if we're not at equilibrium, that's probably even the better way to say it, right? Remember, my concentrations when I'm solving for Q don't have to be equilibrium concentrations. So, right, it depends on the composition of that reaction mixture. It's going to depend on those concentrations or partial pressures, right? Q is part of that equation. There are a couple different ways, some other variations on this equation. Sometimes instead of writing it in terms of natural logs, we'll actually write it as log base 10. So just a couple other variations here. If you're watching other videos or working on homework problems, you may see some of these. So this first one is just converting from log base 10, or sorry, from natural logs to log base 10. So we're taking it and we're multiplying it by 2.303 RT over NF, and then it's the log of Q. And then if we're at 25 degrees Celsius, right, which is 298 Kelvin, then we can actually multiply these out, right? R is a constant, it's our gas constant, 8.314 joules per mole Kelvin. My temperature, we're gonna plug in 298 Kelvin. F is a constant, right? It's my Faraday constant. So if I was to take this number, multiply it by this number, multiply it by this number, and divide it by this number, we actually get 0.0592 volts. It's still over N because that isn't constant, that's still there, times the log of Q. And then again, this is only at 25 degrees Celsius, right? This number here, we're getting it by plugging in 298 for our temperature. So if we're at 25 degrees Celsius, we can also use this equation. So just another variation of the Nernst equation. Both of these, this one and this one, are on your equation sheet. Our cell potential E, just like delta G, does determine spontaneity at any given point. So E, again, as with delta G, determines spontaneity at any given point in the reaction. Remember that the spontaneous reaction is still taking us towards equilibrium, right? We're still moving towards equilibrium. So if E is greater than 0, right? Remember, spontaneous reactions are going to have a positive cell potential. It's going to be spontaneous. And again, that spontaneous reaction moves towards equilibrium. When our reaction quotient, when Q is greater than 1, right, when it's a big number, our cell potential is actually going to be less than our standard cell potential. So if we just scroll up, we can just look at this first one here, right? The log of a number greater than 1 is going to be a positive value. So I'm going to have a positive value over here. So E minus a number is going to give me, E naught minus a positive number is going to give me an answer that's smaller than E naught. When our reaction quotient is small, when it's less than 1, and I know we've typically in chapter 14 and 15 used 10 to the positive third and 10 to the negative third as our cutoffs for big and small. Here I'm just saying bigger than 1 or negative 1. When this is the case, my cell potential is actually going to be bigger than my standard cell potential. And again, just reasoning through our equation, the log of a number less than 1 is going to be negative. So I'm going to have minus a negative number, which means I'm going to be adding a number to my standard cell potential, making my cell potential larger. If we are at equilibrium, my cell potential is 0 and Q is equal to K, right? This is a very similar thing we did in chapter 16 with this equation, right? If we were at equilibrium, this was equal to 0 and Q was equal to K. So my cell potential is equal to 0. We're not moving towards equilibrium anymore because we are at equilibrium. And my reaction quotient is set up using equilibrium concentrations and or partial pressures. So rewriting our equation for that instance, I have 0.0592 volts over N times the log of K. And again, this is set up at 25 degrees Celsius. If it's not at 25, then you have to use the version where you still are plugging in the gas constant, the temperature, and the Faraday constant. We can actually write it here. So I would have RT over NF times the log of K. So if we're not at 25 degrees. So when we have a positive cell potential, we should say standard cell potential, our free energy change is going to be negative. Our equilibrium constant is large, and by large I really just mean greater than 1, and it's going to be product favored. When our standard cell potential is negative, then the opposite of those is going to be true, right? Our free energy change is going to be positive. Remember, those two are always going to have opposite signs. Our equilibrium constant is going to be small, and it's going to be reactant favored at equilibrium. An example for us, we're going to calculate the cell potential at 25 degrees Celsius for the following reaction. When the concentration of lead 2+ ions is 0.15 molar and the concentration of chromium 3+ ions is 0.50 molar. And then our equation is 2 chromium solid plus 3 lead 2 plus, going to 2 chromium 3 plus, plus 3 lead solid. And then because we are at 25 degrees Celsius, we can use this equation. So some of the math has already been done for us, which is nice. Less places for us to make mistakes typing it into our calculator. So what we're solving for here is our cell potential E, right? It doesn't say standard cell potential, it just says cell potential. So that's what we're looking for. This is also unknown at this point, so we do need to calculate that also. And we're going to calculate that from our standard reduction potentials. So you would want to look those up in one of the reduction potential tables, probably the one from the appendix from your text. And I'm just going to write them down here for us. So I have chromium 3 plus 3 electrons going to chromium solid. And these I'm just copying them down right like they are in the table. Remember, they're all written down as reductions, right? It's a table of standard reduction potentials. Reduction potentials. And then my other one, I have lead 2 plus 2 electrons going to lead solid, and its reduction potential is a negative 0.13 volts. So looking at our equation, right, chromium is going to chromium 3 plus, so that one is being oxidized. Here it's written as a reduction, so this one does need to be reversed, right? This needs to be reversed to give the oxidation half reaction. And when we do that, our oxidation potential is going to be a positive 0.74 volts, right? We reverse the sign, we reverse the reaction. So my cell potential at standard state is going to be a positive 0.74 volts plus a negative 0.13 volts. So that comes out to be 0.61 volts. So that's the number that we're going to plug in here for our standard cell potential. Number of moles of electrons transferred. If you need to balance this to be able to do that, remember that's what N stands for. So N, we need to know how many electrons we're transferring. You could balance your reaction. You might be able to figure it out just based on our half cell potentials here, right? Remember this one here that is going away, this one is reversed. And I would have 3 electrons on one, I would have 2 electrons in the other. Remember, it does need to be balanced, so I'm going to have 60 electrons total being transferred. And you could probably get that from here also. Here chromium doesn't have an oxidation number. Here I have one with a 3 plus, but I actually have 2 of them, so I'm actually losing 6 electrons total. Here I have 3 with a plus 2 going to 0, so we're gaining 6 electrons total. So in this case, N is going to be 6. And again, the easiest way to do that might be to just balance these. Remember, those electrons counts have to be the same. This one, of course, this stuff is on the other side because we reverse that equation. Okay, I think we have everything. Oh, we don't have Q yet. We can set up Q when we plug it in, but remember Q is set up like our equilibrium constant expressions, right? Concentration of products on top. So chromium 3 plus raised to a power equal to its coefficient, so as a coefficient of 2. I'm not going to include lead solid, because remember pure solids are not included. And then I have the concentration of reactants on the bottom, also raised to a power equal to their coefficient, so concentration of lead 2 plus raised to the 3rd power. I'm excluding chromium, again, because it's a pure solid. And I'm going to just plug everything into this equation, and we'll plug in these concentrations into Q when we do that. I'm just going to do it all at once here. So we're going to have E is equal to E naught, 0.61 volts, minus 0.0592 volts over 6 multiplied by the log. And then again, this is what we're going to plug in for Q. And you could calculate that part ahead of time if you wanted, but I'm going to have the concentration of chromium, which is 0.50, and I'm going to raise that to the second power. And then that's going to be over the concentration of lead, which was 0.150. Sorry, not point, it was 0.15, not 0.150. Sorry, that was confusing. And then that's going to be raised to the third power. So I'm going to grab my calculator here. Do be careful, it is the log of this fraction, so you want to do all that math first and then take the log of it. This one's going to take a few minutes here to calculate, particularly if I'm talking while I'm typing at the same time. Hopefully you guys are doing this along with me. So I ended up on this side with, sorry, so this part here, I ended up with a 0.018, and I'm just writing that down so we can look at our significant digits. I have 2 significant digits there, and now I'm going to subtract, so I want digits after the decimal point. So when I do that subtraction, right, I'm taking 0.65 and I'm subtracting this from it, I'm going to get 0.59 volts, just 2 digits after that decimal point. Another example for us. So this time we're going to calculate our standard cell potential, our standard free energy change, and our equilibrium constant for a product favored reaction at 25 degrees Celsius that uses the following half reactions. And our 2 half reactions are going to be iron 3+ plus 1 electron going to iron 2+, and then copper 2+ plus 2 electrons going to copper solid. And again, these are both written as reductions. They're taken right from the table of standard reduction potentials. So my reduction potential for this is a 0.771 volts. And then this one is a 0.337 volts. And then this is everything we would be given besides the equations on our sheet. So kind of where to start, I'm going to start by calculating E cell, right, E naught cell, and that's just going to be my reduction half reaction potential added to my oxidation one. So what we need to do is we need to figure out which is going to be my oxidation, which is my reduction, switch the sign on my oxidation one. And then because it says product favored, right, we know that it is going to be going towards products, right, at equilibrium. So I want it to be a positive cell potential. So we want to switch the sign on the smaller one, right? We want a positive standard cell potential. So this one is the oxidation once switched, right? Right now it's a reduction. So my oxidation is going to be a negative, kind of ran out of room there, 0.337 volts. So my E cell, 0.771 volts plus negative 0.337 volts, or minus if you want, and grabbing my calculator. I get 0.434 volts for my standard cell potential. So again, that's just using our reduction potentials, knowing which one is going to be the oxidation if I'm going to have a product favored reaction. Basically, I want a positive value for my cell potential. To calculate my free energy change, we're then going to use this equation, right? My free energy change is equal to negative N times the Faraday constant multiplied by my cell potential. We do need the number of moles of electrons transferred, right, N, and remember our electron counts have to be equal. This one, of course, is switched in the other direction, so these things are on the product side, but I'm going to have 2 moles of electrons, right? I would take this equation, I would multiply it by 2, and then I would have 2 electrons for each half reaction. So N is going to equal 2 moles of electrons. And then my Faraday constant is on your equation sheet. And then you can look at the units a couple different ways just to make them work out. I'm going to do the joules per volt moles of electrons, right? It is actually coulombs per mole of electrons, but I know that 1 volt is equal to a joule coulomb. So then doing a substitution so our units work out, we get this version, which is again on your equation sheet. So you don't need to remember that. So plugging everything in, my free energy change is equal to negative 2. Let's actually write moles of electrons so we can see our units. And then my cell potential that we just calculated. And then units, right? Moles of electrons are going to cancel, volts are going to cancel, and I'm going to be left with joules, which is a unit of energy. We'll end up converting it to kilojoules, but that's what we're going to have in the meantime. So grabbing my calculator. And I end up with, and I'm just going to write it with all the digits, and then we'll round it here and get the right sig figs in a minute. I just want to double check the number here real quick. And I got a negative 837.626, yeah, 62, that's a 2 joules. And then I am going to round it to kilojoules and get the right number of significant digits. I want 3 significant digits, and when I convert it to kilojoules, right, we want to divide by 1,000, move that decimal place over 3 places, so negative 83.8 kilojoules.